Alright, here is the big video that we lost all the audio for because my headphones ran out of battery. That's at least, or Bluetooth just suddenly paired it up with my phone. I don't know what the heck happened with with lecture 15, but lecture 16 has no audio. So here's the preamble. I've already done most of this coding with lecture 16. You can see videos of it where I'm actually live coding a lot of this stuff. I didn't re I didn't undo all of my code and redo it again, so I'm just going to point out what I did last time around. But if you want to see the original me generating the code video, I've left it up. I think I'm going to rename it silent or something like that. What we're talking about this video is actually we're going to be talking about how programs are actually created, what happens when you go to compile your program, and preprocessor instructions and casting. Now, casting is going to be how we say, no, we've already looked at casting a little bit. It's when I called malloc and I said, no, it's not a array of bytes, it's an array of characters. I put that parentheses with a char star in front of it, in front of what I'm doing, and that says, no, treat this as a pointer to characters, not random bytes, not integers, but characters, a pointer to characters. It is, I can tell the compiler, no, I'm saying it's not an integer, it's actually a short, or no, it's not an integer, it's a long. So things like that. The preprocessor instructions are also can get a little funky, so let's go hopefully fairly slowly. When we compile our code, we haven't had to really worry about this often. Every once in a while you may have gotten a linking error, something like that. But we idea is I have some high level language, some actually text file that I write that I pass to a compiler. The compiler knows what to do with this. It it figures out what those instructions mean, turns it into bytecode, or it turns it into machine instructions. It turns it into binary instructions that the computer can use. And so I have this one-to-one mapping between what I wrote in a human readable format to what the computer needs to read. There is this translation from, it's like if I'm translating from so if I give you some really crazy math problem, I can succinctly describe that crazy math problem in math, but most of you, I'm assuming, if you're like me, would not understand what the hell I'm saying, right? If I give you a whole bunch of Greek letters, you'd be like, what is that? So what do? I describe the problem in English, maybe give some examples, and then you can actually do the math problem, or you can at least talk it out. That is what we're doing with compilation. It is human readable to computer readable. That's what we need to, that's the translation that we're doing. But what we didn't talk about is that it actually, well, barely talked about, is that it forms a three-step process. So first, the computer can't read the source program, so I need to compile it. But before I compile it, I do a pre-compilation stage. I do some bookkeeping, I do some preamble stuff. We'll look at what those things are, but there are some things I need to do before I go to compile. Then I compile my code, and once I've compiled my code, I need to hook everything up again because I may have multiple different files. I might be pulling in some library, something like that. And so I need to point everything to the right thing. So it's the equivalent of I set up my assembly line as stage one. I actually build the parts of my car, stage two. I hook up the parts of my car, stage three. People are not building the headlights in the factory where they're actually building the car. They build the headlights separately and then they hook it up to the rest of the car. That is what this third stage is. It's the linking stage. So, in case you're wondering, so Grace Hopper, if you've ever heard the name before, Grace Hopper is the person that does the very first compiler. In 1944, by the way. So, pretty much the moment they start having a computer, someone goes, damn, that's a pain in the ass, and makes a compiler. So, good for Grace Hopper for figuring that out first. She's a badass in computer science. It has an entire conference named after her. In the Mark I, in 1944, she comes up with the idea of compiling code because writing computer code as binary is terrible. There's no way computer science would have taken off if it wasn't for this idea that you write it like a human would write it, or at least hopefully similar-ish to what a human would write. Then you convert it over to what a computer can use. And as long as that mapping is one to one, as long as there's no ambiguity in that and how you convert from original syntax, the code that we write in C, let's say, to what the computer can read, as long as there's no ambiguity, you're fine. And so there's this art form for making a computer language to avoid any kind of ambiguity, any kind of problems that might arise. It's very precise. There's no like sort of gotcha, sort of maybes in the language. It does certain things a particular way. Also, she's also famous for I want the story to be the original story to be true, but it's not. Unfortunately, when I looked into it, you will hear a version of this story. The version of the story is she finds her and her team find the very first computer bug, and by computer very first bug in a program, they literally mean a bug. A moth flew into one of the vacuum tubes of their computer, fried itself, and shorted out the circuits in the computer, and they were wondering what the heck was going wrong with with the computer, why it wasn't working anymore, and it's because a bug fried itself and shorted it out. The idea of a bug in some kind of system predates that. That's why they found it so funny that they actually had a bug fall into their computer and crashed it. But there was an actual literal bug that she found, so I always find that funny. So here's the compilation stage. I start off with my source code. I normally compile it and make object code. That is code that is almost it's binary code, but it's not fully hooked up. Then I hook up all the parts of that binary code so they all know how to communicate with one another, and then I get executable code. Executable code is what exe stands for. When I compiled my code, I got this file called an exe, and all computers are able to just run that code. It's not like a Word document where you need another program to interpret that file. That is designed for the computer to be able to read and use. So when I run my compiler, I convert it to this source. I go to from source code into object code. I link all of these different object files up, especially if I have multiple files, and then I execute it. The reason this example is here is it'd be a prime example of what I need to link up. The IO stream code is somebody else's code. I didn't write it. All this time you were doing hello worlds or using printfs and that sort of thing. You didn't write this. Somebody else wrote it. I just need to know where this is located and hook up what this instruction says when I call cout or when I call printf. I need to know where printf is defined. It's defined up in here. And so I will compile my code, fine. And when I link, it says, hey, where the heck is this printf defined? Oh, it's defined up here. Go to this other file somewhere else in the system and pull in that code. I will make one gigantic file with, unless I'm using a dynamic linking library or DLL, but traditionally it makes one gigantic file. It will take all of IOStream, all of that code that somebody else wrote. It's binary code, so I can't even look at it, but I will take that binary code and shove it at the top of my program. I will have IOStream in my program. I will have all the code I wrote in my program. Every one of these includes will make your program, the exe that I'm generating, bigger and bigger and bigger. It wraps up everything. It's this giant blob of code. In the end, it's one file with everything in it. All the LinkedIn libraries, all the different code that you wrote, any kind of anything special that you had, it's built into this large executable. And that's what the linking stage is. It pulls in all these disparate parts, wraps them, duct tapes them together, wraps them all up into one cohesive thing. So I have one file that has everything I need in it. It's not spread out over a bunch of different things. Everything I need to run that program, other than like an external file, like a file I'm reading in, but all of my code is in one place. I don't have to find anything else on the fly. But before I do this, I have preprocessor instructions. So C is, in its wisdom, it actually makes sense at the time. Before I got going, I need some way of making sure things are set up correctly. Especially when it comes to header files, where if I include the same header file multiple times into my project, bad stuff's going to happen. So I need to make sure that things are set up the right way, and that's where preprocessor instructions come in. So this is stuff that's done before I compile. So pre-compilation. So the preprocessor, so if I put a preprocessor instruction, that's the stuff with a hashtag in front of it, the pound sign, if you are old like me and don't call it a hashtag. A preprocessor instruction is before I get going, do this. So let's, we've, you know, when, so, okay, I wanted to point out the fact that the assignment solutions should be posted when we're doing this. If they're not, please remind me, by the way. I like pointing this out. So we're going to be looking at this one at a time. We're going to look at some conditionals. We're going to look at some what I call macros. I think other people call them macros as well, because I wouldn't have picked that up on my own. These things that I can do before I compile. I can actually do a lot of fancy tricks to speed up my program, and people get really crazy with preprocessor instructions. So I will have my source code. I will modify my source code with a preprocessor. I will then compile everything up, and then I will do make my object code. And after I link it up, I'll get executable. So I will create the file containing all of the text that I'm going to be using, but the preprocessor instructions will do other things. It will do things like if, like this right here, it will take the entirety of iostream.h and dump it on the top of this file here. So this one file will actually have all of iostream inserted right there. It's inserting iostream.h right on the top here. That's what each one of those include statements do. When I go to link it, it says, hey, I have this thing, I have this prototype. I have this little stubby function up here. Where is that actually defined? Oh, it's defined all the way over here in iostream.cpp, or whatever my compiled code is. Every time I have something with a pound sign in front of it, or the hash table, the hash, call it hash, yeah, hashtag in front of it, I will do that instruction before I do the rest. So it will convert all of this stuff into a bunch of instructions, and then I will compile afterwards. So we're going to look at pre-compilation first, but let's look at my horribly, horribly ugly diagram. We're going to be looking at something called Pixel as a class in a second. So let's talk through that first. So so I will have a file, pixel image.cpp. I'll have another file, let's say 2dtest.cpp. Two different CPP files. Each of those will have something that says include pixel image.h, or maybe include standard afx.h, right? Any of those include files, which means I stuff this pixel image.h at the top of, just in front of this. What I don't want, and what I'm going to be producing at the very end, is one gigantic file with all my code in it. So if I include pixel h here on top of pixel image.cpp, and I also include it here on top of 2dtest.cpp, I'll have pixel image.h twice. I would have it here, and I'd have it here. I don't want that. What I want to have is it included once. The first time I include it, and every other time I try and include it, I leave it out. But I still know, because it's at the very top of this one file that I'm generating. So pre-compilation is I'm going to be doing a lot of little tricks. So I'm including a file, but only and exactly once. As long as each of these things include this header file and it only gets inputted in once, I'm fine, because it means all of these classes, all of these CPP files know about it. I just need to make sure that all of them can put that in there. The kicker about C++ is that there's no way to know the order of compilation. I could compile pixelimage.cpp first and then 2dtest.cpp afterwards, or it could be the other way around. I might include 2dtest first and then pixelimage.cpp next. I don't know the order in that's going to happen. That's the problem. If I don't know that order, how do I know which file needs to include pixelimage.h? I don't know. So I have to include it for both this has to include pixelimage.h, and 2D test has to include pixelimage.h. And then I need some cute way or some intelligent way of only including this once, the very first time I hit it. So we'll look at that in a lot more detail soon. Including in this pre-compilation is I might want to define what a byte is as a variable type. It might be a character, right? A character is exactly 1 byte. We've said that that's the only basic data type that we have that is exactly 1 byte. So I may not want to put the word char everywhere because I do not want to accidentally think that a color I'm dealing with, if I have a red, green, and blue set of values, I don't want to think, oh, it's a char, right? The color red is a character. Like, that makes no sense. It's not the letter C. It's some numeric value for what color red it is. They're both just a byte, but I need exactly 1 byte, and the only variable that I have is a char that is exactly 1 byte. So what I could do is say, I'm going to put in the word byte here. This is a new type of data, and everywhere you see the word byte, that's what these pre-compilation things will do for me. Every time you see the word byte, stick in the word char. The computer needs to know it's a char. You don't. The human reader needs to think it's a byte. The human reader needs to think it's a color or an RGB color or whatever you want to call it. The human reader does not want to see the word char everywhere. It's going to screw us up. We're going to think, oh, it's a character. It's the letter of the alphabet. It's not. I want a char because it is 1 byte in size, and that's the only variable type that is 1 byte in size. If I'm using a bunch of, we're going to be talking about bit flags soon. If I have a bunch of bit flags, how do I do a char? I want a bunch of bit flags, let's say 32 of these darn things. It's not an integer really though. I want a bunch of bit flags. I want to call it something else. It'll still be an integer, but I want to redefine what the name is. All of this to say, all of these kinds of instructions are everywhere you see the word byte, replace it with the word char when you go to compile. So just before you compile, hot swap, find and replace. Every time you see the word byte, put the word char in there, done. The human never sees this. The compiler will do this just before compiling all the code. It will hot swap the word byte everywhere in all of my code with the word char. And it'll just do that before, and you won't even need to see that. That is what a preprocessor instruction does. So, by the way, in case you wanted to see, here's my improvised whiteboard thing. When I go to compile, I compile foo.cpp, I'll compile it, I'll make an object file. I compile bar.cpp, I'll make an object file. And at some point in time, I need to hook these things up. They need to know about these other object files. So I have a bunch of object files. I need to be able to point to the right object file. And the only way to do that is to all have the same header file that they reference. So here is, I could, and this is one thing I could do, I could put every single thing I need for my header file in one file called allstuff.h. It may include a whole bunch of different header files. And foo.cpp includes allstuff.h, bar.cpp includes allstuff.h, bar.to.cpp includes allstuff.h. They all include the same header file. Doesn't matter which order they come in. I will only include it the very first time I hit this. So foo.cpp will include allstuff.h, bar.cpp won't. I needed to not include allstuff.h. That's what that pragma once was all of this time. Every time we put that pragma once in a file, it was to make sure that I included it once and only once in my file. So when I call bar.cpp and I include allstuff.h, if it was already included in another file, I leave it off. I just don't put it in. If I try and include it here, it's already in there, leave it off. It's right here. I know that I included it somewhere. I can still find it because it's one gigantic file, read top to bottom, but I only include it once. And here is, we'll look at this in a bit more detail soon. Here is the original way of making sure we only include it once. We say, if this variable here, allstuff_h, is not defined, if not defined, then I will define allstuff_h. and I will do all the stuff for the header file. And at the very end of the header file, I have the end of my if. So if all stuff underscore h is not defined, include all of this stuff. And I also define all stuff.h. And the next time I try and include this file, what happens? If it's not defined, well, it is defined. I defined it the last time I included it. So I leave off all of this stuff because it's in between this if and def and the end, right? All of this stuff is only included exactly once. That's how the traditional way of including precompiled headers are. This quote unquote variable that I have is not actually really anything at all. It is, by convention, I name it the name of my file underscore h just to be consistent. But it is, if I've included this file before, then don't do anything. If I have not already included this file before, then define this value and include everything. I include it only once. So here are the kinds of things we have in a preprocessor instruction. We have comments. Those are actually preprocessor instructions. You just didn't know it. There is no need for a comment to be in my final code. They're for humans to read. I don't care about the compiler doesn't care what the words you're saying are. All of those comments just get completely ripped out. Every single one of them. They don't see your comments. We have includes, like our include iostream.h. We can define new terms. I can define what a byte is. It's a character, right? I can do this if not defined or if defined, right? If the variable is already defined, do something. If the thing is not already defined, do something. I have if statements. I can remove entire chunks of code with this. If this thing is, if debug mode, do a bunch of stuff. Else, do a bunch of stuff. And here's our pragma once, right? Our pragma once was allowing me to only include the file once. The reason you don't use pragma once everywhere for all your code, the only reason is this dates back to, I guess, the 70s, maybe a bit later than that, but it's pretty original for C and C++. The pragma once is after 2010. So if you don't want to worry about, what age of your compiler is, how old your code is, that sort of thing, if you're worried about backwards compatibility, then that's why you wouldn't use the pragma once. Not all compilers support it, for example. It's the only reason you wouldn't use it is because the first way, this way, is so old that everyone still uses it. This way is sort of the new way, and it's still catching on, the pragma ones. Okay, so comments, they're only for you. All right, who cares? No one else needs to read your comments. In fact, you don't want other people to read your comments. One of the problems that Google has on a regular basis is that when they release code or they update code, people go trolling through all of the JavaScript that they have, and the comments have to stay in the JavaScript. They can try and rip them out, but any kind of strings, they can try and deduce what's going on with the code by sort of reverse engineering things. And if comments stayed around, they could actually look at it. If comments stayed around in your C++ code, they could look at it. You actually want to remove the comments to make it harder for other people to reverse engineer what you're doing, first of all. But second of all, the computer doesn't care what your comment is. It's for you or for other programmers. They're really important, but they're for you or for other programmers. The include thing we've already been doing, that will take the chunk of file like iostream.h or assert.h. It will take that entire file and just insert it at the top of wherever that include statement was. It will insert it at that location, because what we want at the end is one gigantic single file. The source file includes all the headers, and it will look as one big chunk of code, one single set of code. And you don't have to really worry about this, because you never look at this actual object code at the end. This is for the computer to use, not for you. So this allows me to make one giant file at the end. But other than that, you do whatever you want. We can define certain things, like if I don't want to define pi a bunch of times, I could make a constant variable. That would be fine. That is our new sort of way of doing things. But I can either make a constant variable, and like a constant, I should say, and set it to 3.14159, whatever the number I want to have is, or I can just define pi as that. Everywhere I see the word pi in my code, when I'm compiling it, I will replace the word pi with this number here on the fly. There's no checking, there's no nothing. It is just it's a find and replace. Everywhere I see a pi, plop in this. That's it. That's what a define does. That also leads to problems with our defines, but that was the old school way of doing things. Rather than having yet another variable around, I'm just going to hot swap. Every time I see this variable, this word here, I'm going to plug in this word here. It's really to clarify your code, right? It's for the programmer's use, it's not for anyone else. I don't want to type in 3.14 blah blah blah, because if I change and add 2 extra decimal points, I'd have to change it everywhere. If I have this value here and it means 2 different things, I don't know which one I'm going to replace. I think I had one of these cases recently where I had a variable, it was set to like 20, but I had two arrays of size 20. And when I wanted to change only one of those arrays to size 10, would have to go through every single one of those arrays, every single time I see the number 20 and go, which one is that for? Which 20 is that for? Is it for array 1 or array 2? This says, okay, every time, if I want to have 2 different versions of pi, I have pi 1, pi 2, 2 different values of pi, and I don't mix them up because it's literally called pi 1 and pi 2. Even if they are the exact same value, I have 2 different defines here. It just makes my life easier. I want to define it once in one place and not repeat myself. So I only want to include this one variable. And it allows me to replace things on the fly. Okay, so I can define a particular name like a is equal to 1, 2, 3, 4, and everywhere I see a, I'm going to get 1, 2, 3, 4. So int p is equal to 1, 2, 3, 4 times 2. The actual code that the compiler will see is int p is equal to 1, 2, 3, 4 times 2. What the issue is if a is misdefined, when I go to compile it, I'm going to get like 4,000 errors. Not one error in one place. It would be if I would 1, 2, 3, 4 E. Let's say I'll have an E here. I'll get a compile error here and here and here, and every single place I use a, I'll get a compile error for this being wrong. Not in one place, but everywhere. And so that is a potential problem. So very traditionally, if I'm using a macro code, I use all uppercase. And sometimes I'll prefix it with 2 underscores just to show that it is a macro. You don't have to do that anymore, but it's all uppercase for sure, showing that it's a constant. So it'll be A, 1, 2, 3, 4. There's no equal signs, there's no semicolon, because it is literally, this is not code that I'm executing. This is not code that I'm compiling. This is everywhere I see this here, put 1, 2, 3, 4. That's it. It's not code that's actually run. It's just a find and replace. Okay. By the way, it can be a find and replace for other things, like here's the absolute value of x. It will, every time I have absolute value of something, so let's say absolute value of var2, I will replace this whole thing. var2 will stay around. It'll be everywhere I have an x, I'm going to put var2, hot swap with each of these things. And I'm going to, instead of putting absolute value of var2, I'm going to put in this with var2 instead of all the x's. So it will end up being this line right here will be var1 is equal to var2 is less than 0, question mark, minus var2, colon, var2. It is going to plug in everywhere I have an x before, I'm going to plug in var2, 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 var2. This allows me to pretend it's a function. That absolute value now looks like a function. It takes in a variable, it spits out another value, it acts, looks, and behaves just like a function, except it's not. It is just literally an inline, it's a ternary statement to get the absolute value. I don't need to call a function per se, I'm just putting in this expression. What's really nice about this is every time I call a function, I have to do what's called, It's a function call, so I have to put something on what's called the call stack. I have to do a bunch of stuff. Every time I call a function, I have to do a bunch of bookkeeping. This doesn't have to do that at all. It is, I'm going to replace this thing here with a ternary expression. I'm done. It's a lot faster computationally. And it keeps my code nice and tidy because what I don't want to do is write this 1,000 times or even 20 times. I don't want to write this entire thing because if I want to change it, it's a big pain to change it. I could change it right here, or maybe I did it wrong. Let's say I put the negative in the wrong place. I'd have to change it 20 different places, or I can change it one place right here and it works. Okay, so it's actually much faster than calling a function, but again, if I have any mistakes in here, I'm going to get 20 or more errors, right? Every single time I used abs, I'm going to get the error in that place, not in this one place, or not where it's defined. We'll also look at some red-green values. So let's say I want a byte. Okay, so I can define a byte as a character, and so every time I use the term byte in something, character. So right down here, that's char, star, for example. I might want to have a red, green, blue value, which is an integer, which is 4 bytes, right? I could then get the red value from a red, green, blue value. So I'll take an integer, I'll get the red value by saying, give me the pointer to the front of the red, green, blue value. So here is the front of my red, green, blue value. I'm going to say it's a byte pointer. So it is instead of just one number, it's actually an array of 4 characters. And then I'm going to say, okay, move one position over. What's this value right here? So what get red in this case does is it says, I'm going to this pointer. It's actually an array of bytes, which is actually an array of chars. A byte is a char, so it's an array of chars. And I'm going to go to position 1 in that array. Boom, I go over here and I return whatever this is. And that would be my red value because the RGB should be ARGB, alpha, red, green, and blue. So let's say I have a red, green, blue color of 244. This is 0, 0. So 244 is only the blue is colored. The red and the green are both, in this case, the alpha, the transparency, the red, the green, and the green are all zeros. And then the blue is 244. And so what I expect to get in this case, I would get, if I use a number 42, this is the example for 42. It's going to be 244, whatever this, for this number down here. Can I do that with 255? Yeah, so it's going to be a 120, 128, and then a 64, and a bunch of almost all ones. Most of these are going to be ones at the front here, and maybe not so many ones over here. It's going to be whatever 244 is in binary, and if I call get red for this color, this thing should return 0. If I made a function called get blue, it would return 244. If I had a function called get green, it would return 0. So we'll look at this in live code, and if you don't believe me, especially if you don't believe me, in a second. So I can also define things. So I can define whether my code has been included or not. We've already looked at where this gets used most. The defining of things is a way of getting our little our header file preprocessor template or header block, right? To make sure that you don't include the same file multiple times. It doesn't really affect the code. I don't actually say what my code is actually going to be defined as. It's defined as something. I could set it to some value, but I'm just defining it as something. It could be 0, it could be 1, I don't know. And I can check to see if it's already defined or not later on, which is the nicety of it. And so I can check to see if it's not defined or if it is defined, and then do different things with my program with that. So I can, if I define something and then I say, if it's defined, do this. If it's not defined, do that. It allows me to do some interesting things with my code and make sure that my code doesn't get included a header file doesn't get included multiple times, for example. So here would be, I'm going to define what double is. If double is defined, then the absolute value of double A double B is going to work. Otherwise, I'm going to use floats, right? And what I could do is if I just remove that double on the front, then suddenly the absolute value is defined a different way. All I need to do is comment this one line out. Double will no longer be defined, and then I'll be using this statement down here. For the time being, its absolute value is defined this way, but if I comment out this double line up here, then absolute value will be defined using floats instead. It becomes really useful in certain weird places. So this is the classic. Here's my header block, right, to make sure I don't include the file multiple times. If my functions is not defined, then I'm going to define it. Then at the end of my file, I have an end if. So it's if this is not defined, sorry, define it, do a bunch of stuff, end my block. If it is defined, leave all that stuff out. Here's the other weird thing. This is why people love C code. It allows me to do some really nice things when it comes to me building for the Mac, me doing a debug build, me doing a release build, me building for Windows or Linux or any number of other things. I can define what kind of build I have. For example, if I'm doing a debug build, maybe I want to do a printf statement. And if it's not a debug build, I want it to do nothing, or I wanted to say it's a release build. You've actually already seen, you may not have realized that you've seen this in action already. The assert statement we've been using all term does this. It checks if it's a debug build or not, and that's a particular define. So am I in the release build or not? Am I doing it for final end product or not? If it's in release build, don't do anything at all. The assert does nothing. It's actually ripped out of the code. And if it's in debug mode, I assert that this is true, otherwise explode. Otherwise cause a breakpoint to go off, or cause it to some kind of failure. That's what an assert is. It is actually removed from all my code when I make a release build, for like I'm making a final game. My assertions will be just removed from my code because of how these defines are working. I will check to see if it's debug mode. If it is, the asserts stay, otherwise they get removed. I could also have something like if Mac build, call a Mac only function here. Else, else if Windows build, then call a Windows only function. Else, then call a Linux only function. What I could not do without this, I couldn't even have the syntax for a Mac only function here. If it wasn't, like if I'm trying to build on a Windows machine, I can't even have the syntax for a Mac only function in my code, because it doesn't even know what that function is called. I need to be able to rip out code that only goes onto a Mac and is only for the Mac, or rip out code that's only for Windows before I try to compile. If I don't, I'm going to get a compiler error. So I can have if Windows build, do this, otherwise do this. I can have Windows specific instructions, Mac and specific instructions, and only include this one place or another. So I may have, let me think of a good example of it. Printf statements don't really work that well, but if I'm doing a painting program, so I have a Windows only painting program and a Mac only painting program, I want to call draw rectangle in both cases. But what I want to do is have draw rectangle as a function just defined, and in half the code I'll have a if Mac build, do this for painting a rectangle, and then I'll have an else statement for how to print a rectangle if I'm using a Windows build. And so which code I actually use at any time depends on whether I'm compiling on a Mac or Windows. It makes it really quick and easy to do different builds of the same code without having to go around and change all your code yourself. You just have it so that you have it in these kinds of statements, and then when I go to build for a Mac, it does it. If I go to build for Windows, it does it. I do this if it's Windows, I do this if it's Mac. I can also have an error message. So if I just put an error message, this error message will be printed, right? Fairly simple. So my compiler, my assert statements could be this, right? If debug build, error, otherwise don't do anything at all. That's how my assert might be defined. just leave it out otherwise. Here's actually what happens with an assert. So if I'm in debug mode, I define assert to be x if x is equal to 1, do nothing otherwise, cause some kind of massive error, like cause an error statement. Otherwise, assert x is just the value 1. I'm just going to put a 1 sitting around in the middle of nowhere. That's all it's going to do. I can do a Windows build and a Mac build as well. They're extremely useful when you're actually building large systems. So finally, we're going to get to casting now. I'm going to finish off. Actually, let me pause for a second. We'll look at casting in a second. I want to make sure that the videos for lecture 17 don't include the casting, because I want to look at some actual live code. So hold on 2 seconds while I'm going to stop the video. I'm going to make a new one in a second. We'll pick up either casting or the live coding in a second. Thanks.